everyone, my name is Christy Mancuso. I'm an isotope ecologist, and this is SOFA Science. I wanted to welcome you to my living room, and in particular, I wanted to introduce you to my sofa, right behind me. I've had my sofa for a number of years now. I bought it from IKEA when I first started grad school in Salt Lake City, and it's been a really good sofa. I never would have imagined that it would have lasted from moves from state to state, from apartment to houses, and it's really held up great. And I have definitely been very lucky to have a comfortable couch to sit on over all of those years. And as you might be able to see, or maybe not because it's right next to me, I have a quilt that I keep on my couch all the time. And this is a quilt that my mom and I made when I was finishing up graduate school. And it represented a bunch of t-shirts that I had collected from high school all the way through college and grad school. And it was a really nice way to get to capture some of those memories that I had, but no longer could carry around that many t-shirts. In particular, one of my favorite t-shirts, I hope you can see it, is of this little pig, and it says, "Please don't eat me, I love you." My college roommate Stephanie gave me this t-shirt, and I just loved it because I love pigs, but at the same time, I also love bacon. So it's kind of one of those conundrums that I have in my life. So now that you've gotten an introduction to my sofa and my living room and some of my favorite items, let's get down to talking about science. And today we're going to be talking about CSI. And I don't mean the television show that was on CBS. I mean CSI, as in crime solved with isotopes. And I'm hoping by the end of this talk, I will convince you that CSI might have a new acronym. Now today I'm going to be telling you a story. And it's a little bit of a gruesome story because it starts off with the discovery of human remains. It works through a bit of mystery trying to figure out who the remains belong to. And ultimately it has, spoiler alert, happy ending when they finally are able to identify the remains. So let's get into our story. I'm going to paint you a little picture. Our story takes place all the way back in 2000, almost 20 years ago, in Salt Lake City out by the Great Salt Lake. A pair of duck hunters were hunting, and they were close to the Saltaire. While they were there, they found a shallow grave. Upon calling law enforcement out, they discovered that in the grave there were some personal artifacts. There was some bones, a skull, and a lot of scalp hair. What was missing amongst all of this was a clear identification. There wasn't a driver's license or a credit card that said, "These remains belong to fill in the blank." So without a clear identity, what were law enforcement agents supposed to do? Now, you and I can start thinking about some of those television shows that we might watch. And in many cases, the way they approach this is similar to what, again, actual law enforcement agents might do. Now, in our case, the police force was able to find a skull in the shallow remains. And so using a skull, an artist can actually go about and do a facial reconstruction. This is where they look at the morphology of that particular skull, and they're able to recreate what that person might have looked like. From there, law enforcement agents can take that image and compare that to missing person reports in their area. They can also look into things like dental records. These can be very helpful once they have a person in mind to then make comparisons to confirm an identity. Similar to dental records, they can also look at DNA analysis to confirm the identity of the individual. Law enforcement agents can also go about taking a DNA sample from those remains and comparing them to federal databases. While this is an interesting idea, the problem is that not everybody is going to be in a federal database. In fact, many of us aren't. So this might be problematic. Now, in the case of the remains that we found in Salt Lake City, the police detectives went forward with a facial reconstruction. The artist rendered an image and thought that the remains might look like this particular woman. The police then went forward. They distributed this to local media agents, such as the local evening news, and again, local newspapers. Essentially, they urged the public to come forward if they recognized her or could provide any information about this woman. The media started to refer to her as Saltaire Sally because she was found out by the Great Salt Lake and the Saltaire. Now, unfortunately, There weren't any strong leads. No one came forward saying, yeah, that's my neighbor, fill in the blank, or yeah, I work with her, it's blah, blah. So without any strong leads, what were detectives supposed to do? Well, unfortunately, the case went cold for about 8 years. Now, during this time, ecological scientists were starting to do some work using a technique called stable isotope analysis. They were using this particular technique to determine the movement and migration patterns of organisms like monarch butterflies and birds. And as forensic scientists started to hear about this research and see the promise, they wondered, could we do the same thing with human remains? Could we try to reconstruct where a person has come from or traveled from? And so this was some of the work that was being done at the University of Utah. The researchers there were asking similar types of questions. Could stable isotopes be a good analytical technique to figure out where an individual had come from? Now, as these researchers were doing some of this initial work, they really had to think about, well, what kind of tissues might we find with human remains? And these can include things like scalp hair, fingernails, teeth, bones, and in some cases, maybe blood. And so when we think about these different tissues, we think about what are they made of? Well, they're made up of different macromolecules, whether that's proteins, lipids, or carbohydrates. And these particular items are made up of different elements like carbon, nitrogen, oxygen, and hydrogen. And one of the unique properties about these particular elements is that they can have multiple forms. And we refer to these forms as isotopes. Now, I know you might be saying, okay, Christy, you've said this word isotopes to me a couple times, but I have no clue what you're talking about. Well, that's okay. I don't think I really thought about isotopes in any significant place until I was maybe in college. And specifically, I think I heard about them for the first time in college chemistry. But what is an isotope? An isotope is essentially an element that has a different flavor. So it's the same element, but it's just a little bit different. So they have the same number of electrons and protons, so they're the same element, but they differ in the number of neutrons that are present, so they have a slightly different mass. So let's take an example. Let's look at carbon. Carbon is one of the most abundant elements on our planet. And carbon has two stable forms. Carbon-12, which is the lighter, more abundant form, and carbon-13, which is the heavier and more rare form. Now, the thing that separates carbon-12 from carbon-13 is simply one neutron. And this gives carbon-13 a slightly different mass. But ultimately, this has a pretty large impact on the distribution of carbon-12 or carbon-13 that gets involved in different biological or chemical reactions. And carbon isn't the only isotope that is used to answer forensic questions or even ecological questions. Other elements of interest might include things like hydrogen, nitrogen, oxygen, sulfur, and strontium, just to name a few. So now that we have an idea of, well, what is an isotope, you might be wondering, well, yeah, how do they get in my body? So isotopes get incorporated into our different tissues from the foods that we consume and the beverages that we drink. So your mom was right. You are what you eat and drink. So with carbon and nitrogen, these really reflect the foods that we consume, whether that's the fruits, vegetables, grains, or even meats that we consume. And for oxygen and hydrogen, these really reflect the beverages that we consume, specifically the types of water that we drink, whether this is strictly tap water or water that's going to be in different beverages like coffee, tea, or even juices. Both the dietary and the drinking waters that we consume get incorporated into our different tissues, and these leave particular signals in these tissues that relate back to local or regional areas. So now that we have an idea of what an isotope is, how isotopes get incorporated into our body, we can get back to our story. So the law enforcement agents had been hearing about the research being done at the University of Utah, and in particular, a budding company called Isotope Forensics. And they approached the researchers asking the question, can stable isotopes be a useful tool to figure out where Saltaire Sally had come from? In particular, they wanted to know the following questions. They wanted to know, was she a resident of Salt Lake City? If she wasn't, did she move here? And if she moved here, where did she come from? And so looking at these questions and the samples that they had, specifically that really large amount of scalp hair that were with the original remains, the researchers came forward and said, yeah, we think that stable isotopes could be a good tool to help you answer these particular questions. And one of the reasons they felt this way was because they had a ton of scalp hair. Now, scalp hair is probably one of the coolest tissues out there. And I know most of us think of it maybe as like a boring or annoying tissue because you brush your hair, it gets on the bathroom floor, and then you just have to clean it up. But hair is really incredible. As it begins to grow underneath our scalp, it's incorporating those carbon, nitrogen, and oxygen and hydrogen elements into the keratin protein. And once that protein is fully developed and formed, it locks those elements in and it locks in that signal, and it doesn't change over the lifetime of that hair. And so essentially your hair serves as this linear tape recorder or time recorder of information of where you've been. Additionally, hair grows at a really predictable rate. In healthy adults, it grows on average about 1 centimeter a month. So depending on the length of your hair, you might be able to reconstruct your travel history from a couple months to, in my case, in Salter Sally's case, several years worth of information. So knowing this, we might be wondering, okay, well, how do we figure out where they've come from? You've told me that water is one of the ways that we do this, but how? How do we do this? And so one of the cool things about waters and the oxygen and hydrogen isotopes that are associated with them is that they behave in very predictable manners. And specifically, they behave in predictable ways across geographic landscapes. Now, one of these predictable patterns that we can look at is a coastal effect. So as we move from the coastline inward, our values become more and more negative. So let's look at this image. We have the ocean, and basically what happens is water evaporates off of the ocean, it condenses, and it forms clouds. And here we have a mixture of those heavy and light oxygen and hydrogen isotopes. And that cloud moves forward and it gets to the coastline. We might have a rain event. And during this time, that cloud wants to try to drop the heaviest oxygen and hydrogen atoms as soon as possible. You can think about this as bringing groceries in from the car. You want to get rid of those heaviest items first. So that cat litter or that dog food, you know you want to drop that at that front door instead of bringing it all the way to the basement. Well, that's similar to what the cloud does. It drops the heaviest isotopes first, and then it moves on, it's a little bit lighter. We might have another rain event, we drop the next heavy ones, and so on and so forth. So that as we move from the coastline inward, our values become more negative. Other predictable patterns that we can look at relate to temperature and elevation or altitude. And we can take all of these predictable patterns and actually create maps of what we think precipitation or maybe drinking water should look like over a geographic landscape. And this is one example. We refer to these as isoscapes or isotope landscapes. And this one in particular shows the oxygen isotope value of tap waters across the United States. And we can see some of these predictable patterns. We can see that as we move from the coastline inward, our values become more negative. Regions of the United States that tend to be warmer tend to have more positive oxygen isotope values, compared to regions that are cooler and at higher elevations, which have more negative values. So looking at this map, we can start to think about, we can think about Salter Sally. Now, if she was a resident of Salt Lake City, we can imagine that her oxygen isotope values might be more negative compared to an individual who might be living in, let's say, Miami, Florida, or even parts of Texas. So keeping this in mind, there are a lot of different ways that we can use oxygen isotope values to figure out where individuals have come from. And this is exactly what the researchers at the University of Utah did. They took the scalp hair samples, they sectioned them, and they ran them through a machine called an isotope ratio mass spectrometer. This machine would allow them to get the oxygen and hydrogen isotope values from those sectioned pieces of Salter Sally's hair. When they got the results, they were able to create a profile of what her hair might have looked like over time. So in this graph here, we can see time on the x-axis or the horizontal, showing us time 0 being the time closest to death or the time that's closest to the root of her hair, compared to 25, which would be the time about 2 years prior to her death or at the tip of her hair. The oxygen isotope values are on the y-axis, and ultimately what we can see from the profile is that it looks like Saltaire Sally moved quite a bit prior to her death. Specifically, it looked like she had moved back and forth between region 1 a number of times. So using these oxygen isotope values, the researchers were able to compare that to oxygen isotope values of waters in different regions of the United States, and they were able to figure out locations that were consistent with the values that they saw in Saltaire Sally's hair. They were able to map these out, as we can see in this image. Region number 1, the region that she appeared to return to, included Salt Lake City and that Intermountain West location. It also included regions 2 and 3, which spanned Idaho, Montana, and Wyoming, and region number 4, which also spread over a good number of states from the Pacific Northwest, the Southwest, going up into the middle portion of the country. And so this is where a lot of the work came for the law enforcement agents. They were given a number of places to look, and now they had to start reaching out, contacting, and looking for missing persons reports that appeared to match Saltaire Sally. This took a long time, but like I told you, we have a happy ending. In 2012, Detective Todd Parks, who was the lead detective on this case, came forward to say that they finally had an identity for Saltaire Sally. Saltaire Sally was actually a young woman named Nicole Bacoles. Nicole, at the time of her death, was 20 years old. They had learned from her family that Nicole had made several trips back to Seattle prior to her death, which was consistent with the oxygen isotope values that they found in her scalp hair. So without stable isotope analysis, it's possible that Saltaire Sally might still be an unknown, and that Nicole Bacoles may never have been discovered. And so I hope that I have convinced you that CSI no longer stands for crime scene investigation, but in reality that CSI stands for crime solved with isotopes. So I think this wraps things up for us, and I hope that I've gotten you excited about our story today, and I hope that Saltaire Sally has inspired you. For me, the story inspires me to continue asking questions in the realm of forensic sciences. It's an area that I love and that I'm quite passionate about. But my ultimate goal for today is that I hope that my talk and the other SOFA Science series inspire you to ask questions. And these don't have to be big questions. These could be simple questions where you look outside to your backyard and you ask, what's that plant in my garden? Or maybe, why are the local animals behaving in a particular way? And I hope that these questions start getting you excited to look at things, to look up answers, and to try to investigate. And maybe your investigations might bring you to one of my favorite places in Salt Lake City, the Natural History Museum of Utah. When I lived there, it was one of my favorite places to visit for a number of reasons. It had one of the best views of downtown Salt Lake, and in addition, it had amazing exhibits, some of my favorites being the ecosystems of Utah, along with the incredible dinosaur exhibit. They also had a number of really wonderful traveling exhibits, so I highly recommend checking it out. And again, feeding your soul and looking at the exhibits and start thinking about some of those questions that you may have had. So I thank you again for joining me today on SOFA Science, and I hope that you tune in and check out some of the other talks as part of this series. Thanks a lot and have a great one.